700 meters below the surface of the Atlantic, in permanent darkness, on top of an underwater mountain nobody had any real reason to look at closely, a research team pointed a camera at something that, by every rule, scientists thought they understood about the deep ocean. Shouldn't have been there. What came back wasn't a black, mineral-choked chimney-venting scalding water, the kind of hydrothermal vent oceanographers had spent decades cataloging. It was pale, towering, almost architectural, a field of ghost-white spires rising out of the seafloor like the ruins of a drowned city, some of them taller than a 15-story building. More than 2 decades later, it's still the only place like it ever found. Not the only hydrothermal vent field. Those exist by the thousands across the world's ocean ridges. But the only place where this particular combination of chemistry, geology, and geological age has produced anything close to it. Scientists have been actively searching for a twin ever since, using better ships, better sensors, and a far clearer idea of exactly what they're looking for. And they still haven't found one. This is the story of how that happened, what makes the place so genuinely strange, and why NASA, of all agencies, has taken a very close interest in a limestone tower sitting at the bottom of the Atlantic Ocean. The expedition that found it wasn't looking for anything like it. In December 2000, a research team funded by the U.S. National Science Foundation and led by Donna Blackman of the Scripps Institution of Oceanography, Deborah Kelly of the University of Washington, and Jeffrey Carson of Duke University set out to study the structural geology of the Mid-Atlantic Ridge, the vast underwater mountain chain that marks the boundary where the North American and Eurasian tectonic plates, and further south, the South American and African plates, are slowly pulling apart. Their goal was straightforward: photograph the cliff faces along the ridge, study the fault lines, and work out how this particular stretch of oceanic mountain had formed. Partway through the expedition, a camera feed showed something unexpected rising out of the darkness roughly 15 kilometers off the ridge axis itself, in a location where the crust was already more than 1 million years old, far removed from the young, volcanically active zone where hydrothermal vents are normally found. The structures on screen had some superficial resemblance to the black smoker vents oceanographers already knew well, chimney-like formations releasing mineral-laden fluid, but these weren't black. They were pale and strangely luminous, more like limestone than anything associated with a volcanic system. With weather closing in and only enough time remaining for a single additional dive, the team took the research submersible Alvin down for a closer look. What they found, once they were actually down among the structures, was a field of towering carbonate spires, spanning an area comparable to a city block, some reaching 60 meters in height, taller than the tallest hydrothermal formation known at the time. Some vents were discharging fluid around 75 degrees Celsius, while shallower pools trapped in ledges and overhangs sat closer to 50 to 55 degrees, a far cry from the 200 to 400 degree temperatures typical of a standard volcanic hydrothermal vent. The team named it the Lost City. Then, with the weather deteriorating, they had to leave. Once researchers got back to shore and started analyzing what they'd recorded, the scale of how unusual the discovery actually was became clear. Nearly every feature of the site contradicted the standard model of how a hydrothermal vent field is supposed to work. Conventional hydrothermal vents, the kind first discovered in the late 1970s and studied extensively ever since, are driven directly by volcanic heat. Seawater seeps down through cracks near a mid-ocean ridge, gets superheated by nearby magma, and blasts back up through the seafloor loaded with dissolved metal sulfides, producing the dark, particle-laden plumes that give black smokers their name. Lost City sits nowhere near an active volcanic zone. It's positioned on crust more than 1 million years old, well away from the ridge axis where new crust is actively forming. There's no magma chamber anywhere underneath it. Instead, Lost City sits on top of something called an oceanic core complex, a geological formation where slow-spreading tectonic plates tear themselves open along long-lived fault systems, exposing rock from deep within the Earth's mantle directly to seawater. When that seawater penetrates cracks in the exposed mantle rock, it triggers a chemical reaction called serpentinization, in which seawater reacts with a mineral called olivine, one of the primary components of mantle rock. That reaction generates heat on its own, no magma required, along with hydrogen gas, methane, and highly alkaline fluid. When those alkaline fluids mix with the surrounding cold seawater, they precipitate 2 minerals in particular, carbonate and brucite, a soft, pearly form of magnesium hydroxide. Stack up enough of that precipitation over a long enough period, and you get exactly what the 2000 expedition found: towering, pale carbonate brucite spires built not by volcanic fire, but by an entirely cold chemical reaction between rock and water, unfolding slowly over an extraordinarily long span of time. The temperature evidence backed this up directly. Standard black smoker vents blast out superheated fluid in the 200 to 400 degrees Celsius range. Lost City's vents were running at a fraction of that, more consistent with a slow, sustained chemical reaction than a violent volcanic process. And the biology told the same story from a different angle. Black smoker fields, wherever they're found, tend to be dominated by large, visible animals, giant tube worms in particular, clustered directly around the superheated plumes. Lost City had almost none of that. What it had, instead, was an extraordinarily dense population of microorganisms, specifically archaea, coating the interior surfaces of the carbonate chimneys, an ecosystem built around chemistry rather than heat. The implications of that chemistry turned out to matter well beyond the borders of the Atlantic Ocean. Every hydrothermal vent field studied up to that point had reinforced one basic assumption: that vent ecosystems, however extreme, still ultimately depended on volcanic heat to drive the chemical reactions supporting life. Lost City broke that assumption cleanly. Here was a fully functioning ecosystem, generating its own energy source through nothing but the reaction between seawater and exposed mantle rock, with no magma chamber anywhere nearby. The microbial communities living inside Lost City's chimneys don't photosynthesize and don't depend on organic material drifting down from the sunlit surface far above. They consume the hydrogen and methane generated directly by the serpentinization reaction happening in the rock around them, a genuinely self-contained chemical ecosystem running on geology alone. That distinction, a functioning ecosystem powered by rock-water chemistry rather than sunlight or volcanic heat, is precisely what caught the attention of planetary scientists well outside the field of marine biology. Two moons in particular, Europa, orbiting Jupiter, and Enceladus, orbiting Saturn, are believed to host liquid water oceans, sealed beneath thick shells of surface ice, oceans that almost certainly sit in contact with rocky mantle material at their base, much like the seafloor beneath Lost City. If a place like Lost City can sustain a self-powered chemical ecosystem here on Earth, using nothing but rock, water, and geochemistry, no sunlight, no volcanic furnace required, then the same basic mechanism becomes a genuinely plausible way life, or at least the chemical building blocks of life, could exist on worlds that never see direct sunlight at all. Researchers studying Lost City's microbiology have explicitly framed the site as a working model for exactly that kind of astrobiological possibility, and it's part of why NASA has maintained an ongoing interest in research coming out of the site, even though it sits quite firmly on Earth. At first, rushed 2,000 dive left researchers with a discovery and very little else. They didn't know how old the field actually was, whether the towers were fixed permanently in place or slowly migrating, how far this kind of venting extended along the wider ridge system, or whether Lost City represented a genuine one-off or simply the first of many similar sites still waiting to be found. Answering those questions took years and several further expeditions. In 2003, largely the same research team returned aboard the Woods Hole Oceanographic Institution's research vessel Atlantis, this time equipped with an autonomous underwater vehicle named ABE, capable of running pre-programmed survey routes and producing sonar maps of the site at a resolution far beyond what a single submersible dive could achieve. Over the course of that expedition, researchers collected well over 100 rock samples, more than 150 vent fluid samples, and a similar number of microbiological samples, while completing 19 additional dives in the crewed submersible Alvin. That work mapped a dozen distinct vent structures spread across roughly a square kilometer of seafloor, including one particularly striking spire nicknamed Poseidon, standing nearly 61 meters tall. Dating the site turned out to be its own extended project. Early isotope and radiocarbon analysis suggested the field had been actively venting for at least 30,000 years. Later work, combining high-resolution seafloor mapping, photographic image mosaics, and direct sampling, pushed that estimate considerably further to at least 120,000 years, making Lost City, by a wide margin, the longest continuously active hydrothermal venting environment ever documented in the ocean. For comparison, most black smoker vent fields have active lifespans measured in decades, occasionally centuries, before the underlying volcanic heat source shifts or fades. Lost City has apparently been quietly building itself, one microscopic mineral layer at a time, since well before anatomically modern humans had spread across most of the planet. With Lost City's mechanism, age, and biology increasingly well understood, the obvious next question became whether it was actually unique, or simply the first example scientists happened to stumble across. Finding out meant deliberately searching for something similar rather than waiting to trip over another one by accident. The National Oceanic and Atmospheric Administration and the Schmidt Ocean Institute eventually combined forces on an expedition explicitly named In Search of Hydrothermal Lost Cities, surveying roughly 700 kilometers of the mid-Atlantic ridge using a genuinely comprehensive toolkit: shipboard multi-beam sonar mapping, instrument packages measuring conductivity, temperature and depth in the water column, sensors tracking chemical plume signatures, and a remotely operated vehicle equipped with real-time methane detection. The expedition succeeded in locating 3 entirely new hydrothermal vent fields along that stretch of ridge, a genuinely significant find in its own right. All 3, however, turned out to be conventional black smoker systems, driven by ordinary volcanic heat. None of them resembled Lost City. That outcome was scientifically informative even without producing a direct match. It suggested Lost City is either a genuinely rare formation or that the specific combination of conditions required to build it, exposed mantle rock, slow tectonic spreading, sustained serpentinization, and enough geological time for towering carbonate structures to actually form and survive intact, is considerably harder to come by than researchers had initially hoped. In 2023, a research team took a more direct geological approach entirely, using the International Ocean Discovery Program to drill a borehole into the southern wall of the Atlantis Massif, the underwater mountain Lost City sits on top of, reaching more than a kilometer below the seafloor. That depth represented new territory for drilling into this particular type of mantle-dominated rock formation, and it pulled up a long, continuous core sample of altered upper mantle material, giving researchers one of the most direct physical samples yet of the exact rock column feeding Lost City's chemistry, and a new reference point for studying how serpentinization unfolds at depth more broadly. A genuine chemical relative did eventually turn up, just not where or how researchers expected. In 2017, at a considerably greater depth of roughly 3,100 meters on the southwest Indian Ridge, scientists identified a new alkaline vent field driven by the same serpentinization process rather than volcanic heat. They named it with what might generously be called restrained creativity, the Old City. Subsequent microbial ecology studies confirmed the site shares real chemical and biological similarities with Lost City, including comparable archaeal communities. But the physical resemblance stops well short of a true match. At the depth Old City operates, crushing pressure and different local fluid dynamics appear to prevent the kind of towering 60-meter carbonate spires that define Lost City's skyline from forming or surviving. Old City is real, and it's a genuine scientific confirmation that Lost City-style chemistry exists elsewhere on the seafloor. It's just considerably smaller and less dramatic, more modest settlement than Metropolis. A further expedition, led by NOAA Chief Scientist David Butterfield aboard the Schmidt Ocean Institute's research vessel Falkor 2, and equipped with one of the most sensitive methane detection systems ever deployed for this kind of survey, picked up a promising signal near an underwater feature called the Puy de Faux volcano, also along the mid-Atlantic ridge. Instruments detected substantial plumes of methane and hydrogen rising from the seafloor, chemically consistent with what Lost City itself produces. What the team's remotely operated vehicle eventually found at the bottom, though, was another high-temperature black smoker field, venting at roughly 340 degrees Celsius, hot enough to melt lead, and clearly volcanic rather than serpentinite-driven. It was a genuinely significant discovery in its own right, marking the first new vent field identified along that particular 640-kilometer stretch of ridge in over 4 decades. It still wasn't the twin researchers were hoping for. To appreciate why Lost City ended up exactly where it did, it helps to understand the geological feature it's built on top of in the first place. The Mid-Atlantic Ridge, part of a global mid-ocean ridge system that snakes around the entire planet for roughly 65,000 kilometers, the longest continuous mountain range on Earth, and one that spends almost its entire length hidden beneath the waves. The ridge exists because the seafloor there sits directly on a divergent tectonic boundary, a location where two plates are slowly pulling apart from each other rather than colliding. As the plates separate, hot rock from the mantle rises to fill the gap, and as it rises, the drop in pressure allows some of that rock to melt into magma. That magma cools into fresh oceanic crust, which then gets pushed outward on either side as the process repeats over and over across millions of years. In the case of the Mid-Atlantic Ridge specifically, that spreading happens at a rate of roughly 5 centimeters per year, a pace that sounds trivial on a human timescale, but has been steadily widening the entire Atlantic Ocean basin for tens of millions of years. Because the Mid-Atlantic Ridge spreads relatively slowly compared to faster ridges elsewhere, like the East Pacific Rise, it doesn't form a smooth, continuous volcanic dome. Instead, it produces a landscape of rugged fault lines, steep escarpments, and a central rift valley comparable in scale to the Grand Canyon in both depth and width. That ruggedness matters directly for Lost City's existence. Slow-spreading ridges are considerably more likely to tear themselves open along long-lived faults deep enough to expose mantle rock directly to seawater, precisely the geological setup that makes serpentinization, and therefore a site like Lost City, possible in the first place. A faster-spreading ridge, generating smoother, more continuously volcanic crust, simply doesn't create the same kind of exposed mantle window. Lost City itself sits on a specific geological feature called the Atlantis Massif, an oceanic core complex rising from the ridge roughly 15 kilometers off the main spreading axis. Core complexes like this form when tectonic extension along a ridge becomes asymmetric enough that one section of deep crust and upper mantle gets pulled upward and exposed at the seafloor, rather than staying buried beneath a normal layer of basaltic crust. It's that specific exposure of mantle rock, sitting on aging, tectonically quiet crust well away from active volcanism, that allowed a 100,000-year chemical reaction to run largely undisturbed, rather than being buried, reheated, or torn apart by nearby volcanic activity, the way it likely would be closer to the ridge axis itself. The microbial community living inside Lost City's chimneys deserves attention on its own terms, not just as supporting evidence for astrobiology. It represents a genuinely different way of organizing an ecosystem than almost anything found closer to the surface. Nearly every food web most people are familiar with, on land or in shallow water, ultimately traces back to photosynthesis, plants or algae converting sunlight into usable chemical energy, with everything else in the ecosystem feeding on that energy, directly or indirectly. Even the black smoker vent communities discovered in the 1970s, while famous for not depending on sunlight directly, still rely on volcanic heat as their underlying energy source. Chemosynthetic bacteria oxidizing hydrogen sulfide released by magma-heated fluid. Lost City's microbial residents run on a different chemistry entirely. Researchers studying the site have found the chimney interiors dominated overwhelmingly by a single lineage of archaea belonging to the Methanosarcinales, an ancient group of microorganisms that predates complex life by a wide margin, alongside smaller populations of sulfur and methane metabolizing bacteria. These organisms consume the hydrogen and methane generated directly by serpentinization, the same cold, ongoing rock-water reaction responsible for building the carbonate towers around them, converting that chemical energy into the basic processes of metabolism and reproduction, without any input from sunlight or magma-driven heat at any point in the chain. Compared to black smoker vent communities, which tend to support a visible, relatively diverse array of larger organisms, tube worms, crabs, and various mollusks clustered densely around the hottest plumes, Lost City's visible fauna is comparatively sparse. What dominates instead is that dense microbial biofilm coating the interior surfaces of the carbonate structures themselves, an ecosystem built almost entirely around single-celled organisms rather than larger animals. Researchers examining the site have described it as one of very few places on the planet where an entire functioning ecological community can be traced back to a single geochemical reaction, seawater meeting exposed mantle rock, rather than to sunlight, a volcanic heat, or any input arriving from outside the system itself. That self-contained quality is precisely what makes the site such a compelling reference point for astrobiology. A functioning ecosystem that requires nothing but rock and water to sustain itself doesn't need a sun. It doesn't need active volcanism. It just needs the right kind of rock in contact with the right kind of liquid water for long enough. That's a considerably lower bar to clear than most models of extraterrestrial life have historically assumed, and it's part of why researchers studying icy moons like Europa and Enceladus, worlds with subsurface oceans in likely contact with rocky mantle material, but no direct sunlight reaching that depth, have treated Lost City less as a curiosity and more as a working proof of concept. Every one of these searches has reinforced the same basic conclusion. Producing something like Lost City requires an extremely specific, extremely rare alignment of conditions, exposed mantle rock, slow tectonic spreading, sustained low-temperature chemistry, and well over 100,000 years of essentially uninterrupted geological patience. That rarity is part of what makes the original site scientifically valuable. It's also part of what makes it vulnerable. The mid-Atlantic ridge and the wider deep ocean floor around it have increasingly become targets of interest for deep-sea mining, as companies and governments look toward mineral-rich crust formations near hydrothermal systems as a potential source of metals used in modern manufacturing and electronics. Scientists studying Lost City have flagged direct concern that mining activity, or even nearby exploratory operations, could permanently damage or destroy carbonate structures that took well over 100,000 years to form and cannot be meaningfully restored once broken apart. Unlike a coral reef, which can at least partially regrow under the right conditions, Lost City's towers are the product of an extraordinarily slow mineral precipitation process. There is no realistic mechanism by which a damaged section could regenerate on any timescale relevant to human industry or even human civilization. That tension between a site valuable enough to attract sustained international scientific attention and a location sitting in waters increasingly eyed for extraction is very much unresolved. Researchers involved in the site's ongoing study have been explicit that losing Lost City, whether through direct physical damage or disruption to the surrounding geology, would mean losing direct access to one of the clearest working examples we have of how life-supporting chemistry can emerge in total darkness, without sunlight and without volcanic heat. A system that took over 100 millennia to build, and that no known process could rebuild on any timeline that matters to the people making decisions about seafloor mining permits today. Deep-sea exploration has produced plenty of genuinely strange finds over the past few decades. Giant tube worms clustered around black smokers, entire ecosystems living off whale carcasses on the seafloor, bacteria surviving in rock kilometers beneath the crust. Against that backdrop, it's worth being specific about what actually sets Lost City apart from the rest of that list, because strange deep-sea discovery alone doesn't quite capture it. Most unusual deep-sea life still fits within a framework scientists already understood in broad strokes before finding the specific example. Extremophile organisms adapting to pressure, cold, or darkness, but still ultimately deriving their energy from sunlight or volcanic heat somewhere upstream in the chain. Lost City didn't just add another extreme example to that list. It removed one of the framework's core assumptions entirely, that a self-sustaining ecosystem needs either sunlight or a volcanic heat source somewhere in its energy budget. Finding a functioning, long-lived ecosystem that needs neither wasn't a matter of degree. It was a genuinely different category of discovery, which is part of why it prompted geologists, chemists, and biologists to independently revisit their models of the site from 3 completely different angles, rather than simply cataloging it as one more unusual vent field. The age is its own separate kind of remarkable. Most geological features studied on human timescales are measured in centuries, or at most, a few thousand years of relevant activity. An active hydrothermal system running continuously for over 120,000 years, through multiple ice ages and dramatic shifts in global sea level, without the underlying chemical reaction driving it ever meaningfully slowing down, doesn't have many direct comparisons anywhere else in active, ongoing geology. Most long-lived geological features people are familiar with, mountain ranges, canyons, are the product of slow accumulation or erosion over that kind of timescale. Lost City has been actively building itself the entire time, one microscopic mineral layer precipitating out of solution after another, the whole time modern humans have existed as a species, and for tens of thousands of years before that. Looking back at everything that's happened since that first rush dive in December 2000, the most striking thing isn't really the discovery itself. It's how much sustained effort across more than 2 decades, multiple research institutions, several countries, and increasingly sophisticated survey technology has gone into simply trying to find something comparable, and how consistently that search has come up short. 3 new black smoker fields discovered along the ridge, a genuine serpentinite-driven chemical relative found on the opposite side of the world, at a depth that prevents it from ever looking anything like the original, a kilometer-deep borehole into the mantle rock feeding the reaction. None of it has produced a second Lost City. What that consistent pattern of near misses actually demonstrates is how narrow the geological window really is. You need exposed mantle rock, which requires the right kind of slow-spreading tectonic boundary. You need that rock to sit at a depth and pressure that allows tall, stable carbonate structures to form and persist rather than collapsing or dissolving. And you need all of that to remain essentially undisturbed for well over 100,000 years, through ice ages, sea level changes, and shifting ocean chemistry, without whatever formed it breaking down or being buried. Put those requirements together, and it starts to look less like an oversight that scientists haven't found a second Lost City yet, and more like genuine confirmation that the site occupies an extraordinarily specific and extraordinarily rare geological niche. It's a reminder, too, of how much of the ocean floor genuinely remains unmapped in any real detail. Even with modern multi-beam sonar, methane sensors, and autonomous survey vehicles, researchers are still effectively searching a vast, dark, 3-dimensional space for a landmark they can only recognize once they're close enough to see it clearly. A search that gets narrowed down mostly through educated inference about where the right tectonic and geological conditions might exist, rather than through any kind of direct, wide-area detection method. The original expedition in 2000 wasn't looking for anything like this. They found it anyway, purely by chance on their very last scheduled dive before the weather forced them back to shore. Every search conducted since then, deliberate, well-funded, and armed with technology the original team never had access to, has failed to turn up anything that comes close to matching it. At some point, that failure to find a twin becomes a finding in its own right. Whatever built the Lost City, it may genuinely be a one-off, a single extraordinary structure quietly growing in total darkness at the bottom of the Atlantic, built from nothing but rock, water, and roughly 120,000 years of patience.